This is the video for the Hill Street routine for dynamic programming. Over here on the left is the routine. Over here on the right is the display of the hills that it has to go over and the positions of the peaks and troughs. Right, the routine starts out, it says for t of 0, and down here next t to 225, 25 at a time. Well, it's going to go around the outer loop here for each one of these positions, starting at this one and going through each one where we'll say these are poles. Each one of these poles until it gets to the end. That's the outer loop. Starts out in a loop with setting k equal to t, but then adding 25 to k. That's going to mean that it's no longer pointing at this 0 position, but it's going to be pointing to this pole here. Then it says set c equal to the x position of that pole. All right, that would be the horizontal position. Set d to the y for that position. So we have c and d, the x, y positions of a position on this pole. Then it sets, well, first it checks, is d less than 0? Well, the ground down here is 0. You cannot have a point below this ground level 0. So it says if it is, we cannot have this one. So we're going to go around down here to BL, and we're not checking that pole anymore. Well, if it's okay, then it goes down here and it sets the base cost to a very large number. Well, we're going to test each possibility against the base cost. So we set it to a high number so that we know when we find the first possibility, it's going to accept that one, because it's going to be lower than this number. Then we're going to set L to T. That's pointing to here. Remember, K points to this one, L points to this one. It says for J of 1, and then down here it says next J for 16 times. So now we know that we're not only looking at this position for 16 times, but whatever one was before it. 16 possibilities. That'll make more sense when we're out here going between two different poles. Actually, you can understand when we're going to this first position, only one of them is above ground, and that's the original one. Alright, so now we're going to go around to all those positions, and we set A to the X position. At first it's this one. And then we set B to the Y position, and then we check again to make sure it's above ground. If it's not, we're going to go down here to BK, and we're done looking at that position. However, if it's okay, then we have a subroutine here that's going to figure out all the costs for us. We don't want to put the figuring out here because it'll just complicate these loops. So it's a subroutine. We say at that subroutine it's going to take our positions of A, B, and C, D and figure out what the costs are. That would be, say, for going to some position on this pole to some position on this pole, what's the cost? Well, that routine comes back with a cut cost, a fill cost, and a slope charge. And we also have to add to it the cost of the original position before it, because it says it cost so much to get to that position. Now we're moving to another position. We have to add the cost of getting to the previous position. So that's what it's doing here. Then it says if that cost is greater than our base cost, greater or equal, to the base, we'll go to BJ. It's no better than a cost we've already found. But if it is a better, that is a lower cost, we're going to set our base cost to that cost. We're going to set the cost for that position, K, to the base cost, which is really the test cost. Then we're going to set the position for that to L. That's the gist of dynamic programming, is that it remembers where the lowest cost was. So say we're at this pole here. At any one of these 16 positions, it knows what the best cost is going back to this pole, because it remembers its way back. And it's going to do that every time. And it's going to be doing 256 possibilities between these two poles. Then 256 between these two. Always recording at this pole, the next pole, what the best cost back was at that particular, in this case, height. Till we get to the very end. And then it's going to say, well, now how do I get the best cost overall? Well, the last position will say go to here. Then it'll say go to here, go to here, go to here, all the way back to the beginning. So this is the way the routine works for the Hill Street problem. So this is the end of this video about the Hill Street routine for dynamic programming.